for the introduction. Yeah, I wasn't expecting to give the talk until Wednesday, so I had to stay up all night to make sure I knew what I was going to talk about. That's what Olivier would have done. So Anthony asked me to talk about how we polydisperse multiphase flows using quadrature-based moment methods, and so that's what I decided to talk about. I guess it's a good setting for that because it's kind of a mathematical talk, but I try to take out all the math. But it's a method that's really to solve equations with distribution functions, and it's a very efficient way to do that. So I'm going to use, in this talk, I'm going to use gas particle flow as the example. This is some riser simulations that we've done, and so I'm going to, all the ones that we've done and reported in the literature are for monodisperse particles. There's different levels of closure, starting from second order closures. This one was done with the anisotropic Gaussian. I'll tell you what that is later. And then we have something that we just did recently that hasn't even been published yet. It's a Louis Dajanet student. Conditional hyperbolic Human with a fourth order closure. And this is from Jesse. This is a Euler-Lagrange. So when you look at this, you should think that this is what we're trying to reproduce, or the same statistics at least of this flow by using the Eulerian method. And the idea is that the Eulerian method should be cheaper, at least if everything works right and you on large computers. So I'm going to explain how we do this and extend it to polydispersed. Just to get started, I want to show you why you use different levels of closure. Second, if you look at the two pictures for the riser, they look pretty close between second order and fourth order. If you do a more complicated flow, this is the Taylor-Green flow, where we have vortices that circle and the particles are inertial. They start in each of the boxes. And as they spin out, if you do a Lagrange simulation, this is a Stokes number of 5. It's above the critical Stokes number. What happens is the particles in this box get pushed across the boundary. Okay, there's no collisions in this example. And you can see the Eulerian Lagrangian simulations are very complicated. You get very complicated patterns. With an Eulerian model, you can never reproduce this because there's just too many degrees of freedom. Okay, because there's no collisions, there's nothing to drive the particles to some attractor to change their trajectories. So the best you can do is, so if you start at second order, you get this, and you can see there the second order closure. What do you see? Well, all the particles are at the boundaries. Here they crossed over and they accumulate away from the boundaries. There they accumulate at the boundaries. And the reason that is because it doesn't allow particle trajectory crossing. A second order closure just has pressure. And so they try to go through and it creates a pressure at isotropic second order moments. And so it doesn't have the information in it that tells it, well, these are two separate velocities that should cross. If you go to fourth order, actually if you go to third order, you can get a crossing. With fourth order, you can get hyperbolic, and so this, you can see a fourth order allows you to have one crossing. So if you want to have these bands that go crossed, with the fourth order closure will get you the crossings. It won't get you all the details again because you'd have to go to much higher order. So that's the difference. So the question is, we'll have a suite of Eulerian models that can do different orders. And depending on the flow that you're interested in, you could choose an order that reproduces the statistics of the Euler-Lagrange. Okay, so we've done a lot of this, and there's all these publications, and I'll explain a little bit how it works. The main thing I want to talk about today is how to extend this to particle size if you have particles of different sizes, and how do you do the modeling for that? Okay, so we start with the kinetic models. This is a kinetic equation. So I think I've been working with these a very long time. I first met Olivier, someone I met at a conference, I don't know, 25 years ago, we were doing kinetic models in the early 90s. And so this is a standard kinetic theory model, and if you're used to gas particle flow with the kinetic theory model, this is the model for the particle phase. The gas phase, you use the Navier-Stokes equation, and it's coupled together. What's different about this one? Well, I'm going to add another variable. I call it C. I'll sometimes call it size, but it's usually the mass because the mass is conserved. So think of C as a distribution of masses. So you have particles of different masses. And so your kinetic equation becomes a generalized kinetic equation. And so you have the transport term, free transport for the velocity, which is just how the particles move with their own velocity. You have acceleration. This is typically due to coupling with the fluid phase or gravity. And then you have a collision term. And so a lot of the work on polydisperse is in the collision term because you've got to get the exchange of momentum between particle collisions, et cetera. So I just wrote C. I'm not going to tell you the whole Boltzmann-Enskog equation. If you have questions, we can talk about it this week. It's an advantage. But most of the work is in C in the collision term. I'm going to do hard sphere collisions. Again, I'm not going to go into details, but I can tell you how it works. And so we're mainly interested in the moments of this distribution function. And when I talk about moments, I'm talking about what's the volume fraction, what's the size distribution, the mean, the variance, et cetera. What's the mean velocity that you get, that's a moment, what's the pressure, the variance, et cetera. So there's a hierarchy of moments that we're interested in. We don't really want to solve for f. It has a 1 plus 3 plus space and time dimension, so it's too big. So we're not going to try to solve for it. And the moments, though, will just depend on space and time. Okay. I'm usually going to write the moments like this. For the simplest example, I'm going to split the velocity into conditional velocity. So this is the distribution of the velocity given a certain size or certain mass. And then the distribution of particle sizes or masses. And so think of this as a probability distribution functions. It's conditional on size, and this is just the distribution of sizes. Okay. Okay, so what are the moments that we need to describe the flow? So the minimum set of moments. I'm going to mainly stick with just the isotropic Gaussian. The first set of moments you need are what are the moments with respect to size. And so S here is a parameter, and it starts from 0, 1, 2. It's an integer parameter. And it'll tell you 0 order moments are the number of moments per unit, number of particles per unit volume. If this is mass, the first order moment, S equal to 1, is the density of particles, mass density per unit mass, et cetera. And so as you go up, you can use more and more moments to try to get a more and more complete description of the size distribution. So those will be ms. You then need to have information about how the velocity is weighted by size. And so we'll use the same thing. But now we have this conditional velocity. The conditional velocity is just the mean velocity with respect to g. So it's the size. Think of it, if you take all the particles with size c, it'll be the velocity of that, the average velocity of those particles. And then I'm going to only use granular temperature for this example. So I'm going to stick to second order, but just the trace of the second order tensor. So theta will be the conditional granular temperature again. So you take all the particles with the same mass, you take their velocity fluctuation squared, and this is the average of those. Again, so this is a small set of moments, but this is the minimum set you need to describe the flow. Okay, so just remember that when you see, I'm going to have you, so for the notation, if you see non-script U and C, those are conditioned on size. And then these other moments that are script or italics, those are the weighted moments. Okay, so these are all the particles just weighted by, they're weighted by a different factor in front. Okay. Okay, so those are the moments we're going to be using. So question is, what do we do with them? Okay, before I do that, let me talk a little bit about what the moments mean. And for collisional gas particle flows, I'm going to stick with this set of moments today just because it's the simplest set. So this is kind of the minimum set that you need to do particle trajectory crossing and describe a distribution function. So M0 in that case is number concentration. So just the number of particles per unit volume of any, regardless of their size or their mass. M1 is the mass weighted, so that if you think in a monodisperse, it's just rho p times alpha p. So it's the volume fraction of particles times their density. And today you can also have the density be size dependent, but I'm going to make the density constant to make it simple. So it'll be a constant variable. If you look at M2, then you need that to get the variance or the width of the distribution of sizes. Okay. And then M3, you need it to get skewness, whether it's symmetric or not symmetric. So obviously, if you had a very complicated distribution function, you'd need more moments. But here I'm going to stick with these, and just so you can see how it works. It's not hard to add more moments if everything is set up correctly. Okay, so once you have 4 moments for size, the minimum number of moments you need for velocity is 2. Okay, and we'll see their interpretation. That's the velocity based on their number. So you just look at all the particles in the system, and you just weight the velocity. You take an average weighted by just the number of each type. Normally you don't do that, right? Normally you weight it by momentum. Okay, that's U1. U1 is the momentum weighted velocity, and so you can see in the monodisperse, that's what you would use, rho p alpha p times UP. So the first one is number weighted. Just tells you how. So they're different because smaller particles are usually moving faster than bigger particles. Okay. And then for the granular temperature, we do the same thing. Number weighted granular temperature is T naught, and T1 is the normal granular temperature that you solve in a kinetic theory model. Okay, so those are the set of moments I'm going to use mostly today. There's two special cases that you want your method to work for. The first case is I call discrete sizes or binary systems. So suppose you have a system and you have exactly two particle sizes. These are delta functions. One size is mass 1 and the other size is mass 2. And it doesn't change. The whole system is composed of two particle types. In that limit, the distribution function looks like this. It's the number concentration of size 1 plus the number size multiplied by delta functions. Okay. So there are two pieces of unknowns there. There's only two things you don't know, because you know the sizes. You don't know W1 and W2. So how many moments do you need to figure out what W1 and W2 are? Olivia. You need two, right? Because there's two pieces of information that you're missing. So in theory, if you have a binary system, all you need to know is M0 and M1. Because you can change that to W1 and W2. And these other two moments that I've introduced, M2 and M3, they can be written in terms of these constants multiplied by the weights. So you take the constants to the second order, you get and multiply by the weights, et cetera. So they're redundant. Okay. And so if I have a binary system and I use my solver for this, my solver should know in advance that if I solve for 4 moments, I'm still going to get constant abscisses. And I'm going to give that a name. I'm going to call that a consistent solver. Didn't have anything else to call it. So you can think I'm going to have a general solver. I'm going to run it. And if my system has a binary system, I want it to, even though I solve for 4 things, I want it to figure out, without me telling it, that it's got 2 abscisses that are constant. And I'll call that a consistent solver. It should do that because that's in the equation. The kinetic equation has that property. Okay, so that'll be a discrete or binary solver. You can make that as many as you like by adding more moments. The other system is a continuous distribution function. This is more what you usually work with. So you have particle size distribution around some mean and some variance and some skewness. Okay, so then the moments are independent because they depend on the shape of the distribution function. And so when you solve for these 4 moments of this distribution function, they have to be realizable. Okay. So this is where all of the complication comes in when you do the numerical methods, is how do you make the solver realizable. So if you use a standard finite volume solver like in OpenFOAM, you just plug in these equations like you would do in OpenFOAM. If you use first order upwind, you're quite happy because it's realizable, but it diffuses all over the place. So what your tendency would be to do is then to say, oh, let's use second order method. You do that in OpenFOAM or any other CFD code. It's nothing particular. Standard finite volume solver. Then suddenly you're going to get moments that are non-realizable. What does that mean? Well, that means your variance is negative, for example. So that one's pretty easy to see. Or the number density is negative. Typically that's less often. But it's with these 4 moments, it's usually not hard to see because it's usually just the variance that is negative. But if you add a M4, M5, and 6, the constraints on realizability are harder to build into the solver. So we want to have solvers that are realizable, meaning that we don't want to have to check every point. We want to make the finite volume method automatically give us moments that are realizable. So later on I'll show you examples where we have a consistent solver and then we'll check it for realizable solver. So that's what I'm talking about. So keep that in mind when I come back to that. Okay, so how do you get the transport equations? This is where you have all the fun of doing the integrals. I'm not going to do them. I'll just show you the steps because you're probably familiar with this if you've ever done kinetic theory modeling. You start with the Boltzmann-Instock kinetic equation, the one I showed you in the first, and you multiply it. Well, the first thing you got to do with the Boltzmann-Instock equation is you got to figure out what your 2-particle correlation function is. I don't know if everyone's familiar with that. I can talk to you later, but that's a key part, because that's going to determine how your particle interact with each other. For example, if you want to have a buoyancy effect, if you want to have the big particles see a buoyancy from the small particles, you've got to choose a particular form for this, and it's usually not the one you'll see in the literature. Okay, so that's very important. So you have to choose that first. That just basically closes the kinetic equation. So it's a closed kinetic equation. Once you've got that, and Boltzmann-Instock, you'll have a collisional flux and a collisional source term. You formally multiply by c to the s times what is the velocity, direct product to the kth power, whatever. So this is the order of the moments you're going to use. You do the integrals, classical integrals. The ones on the left-hand side are fairly straightforward. It's the collision terms that are more complicated because there's another integral, which is the integral over the collision angles. Okay. It turns out that if you use integer moments, the collision angle integrals are closed. I rarely see this. It turns out it's put in the book I did with Daniele, but if if you have integer values here, you can do those exactly. Most people do the Chapman-Inscock expansion there before they actually do the closure. So you can actually get the closed intervals, and they're exact, and meaning that they don't depend on the form of the number density or the velocity function. And then once you've had that equation, you can also do the integrals with respect to the velocity distribution function. It turns out some of the important terms are also closed with respect to the moments of the distribution function. So it doesn't depend on the shape, it's the moments. And so there's the collisional fluxes. And then once you do that, the ones that are not closed, you can use this quadrature-based moment method. So that's the steps, okay? So you end up with some equations, and here's what they look like for the moment system that I showed you. So, okay, and so if you look at the top, it's just a mass transport equation where you've got the moments of order s being transported with the velocities of fluxes of order s. These fluxes are solved down here. So this equation is closed in the sense that you don't have to do any closure on it. This is the velocity weighted with the power s. This is the ground temperature weighted to power s. And if you're familiar with these things, you'll notice the terms. I put f here, free transport terms. Those come from the v, the gradient v times f term. So those are typically trivial to deal with quadrature method, so free transport. The g term is the collisional flux that comes from adding the Boltzmann-Inscock collision integral. These terms here are due to gravity, the acceleration, and to the buoyancy force due to the fluid, so they're closed. You have a drag term due to the fluid. I just write it as 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 a source term. And you have a collisional source term that tells you how the momentum is moved between different sizes. And likewise for ground temperature, you have free transport, you have collisional fluxes, you have a production term due to flux, a loss term due to drag, and you have a collisional source term. Okay, so I decided not to give you all the formulas because if you need them, I can show them to you. But it's just the form of the equation. Remember, if you look at this is the free transport. Later on, I'll do operator splitting. I'll split this part off. I'll solve just this part plus this part, and then I'll do the other part separately. So the form of the equations is what you need to see when you derive the solver. So we want to have a solver that does consistent size moments, realizable size moments, and realizable energy moments. Real energy moments means the ground temperature has to be positive and some properties on ground temperature. Any questions on up to now? Okay. I couldn't hesitate to show you this one. This is for actually behinds. And people that actually do kinetic theory, probably for Olivier. I said earlier that you can actually do closed forms for the collisional fluxes. And so here I wanted to show them to you. This is the free transport term for the momentum. This is the pressure due to collisional pressure, and this is the viscosity. So if you do the integrals for the ground of pressure, it looks like this. It's got a pressure term that's size dependent, so the pressure for a given size multiplied by the size to the s power. And so that just comes out from the way the integrals are nested. But the important point is this pressure, the particle pressure for size s. So it's got the free transport part, theta, that's the classical part. And then it's got this term here, and this term turns out to be closed. You can get the exact one. You don't have to do a Chapman-Inscock expansion. You get a term. I didn't tell you what E is. E is the sum of the granular temperatures plus the velocity difference between the two, the magnitude of the velocity differences. So this E is known. And these are other just geometric parameters and the velocity, et cetera. So the important point is this is closed. Okay? So we don't have to do a Chapman-Inscock expansion because we have it in terms of the moments that we're interested in. So it's exact for hard spheres. Likewise, granular velocity, this is not closed because you have to do a Chapman-Inscock, but you get a similar formula. So those are what goes into the theory. And then we use the size-dependent straight strain tensor where we take the gradients with respect to US, or the weighted velocities. So, okay. So the important point here is that if you look at these fluxes, if it's a binary system where you put C1 and C2 and you do the integral, all of these pressures are going to be complicated, are going to be connected together. So if you look at segregation of particles, the pressure is going to be strongly dependent on all the particle properties in the system. The usual models that you see in the literature, they're done separately. You just do P and it doesn't depend on the other phase. Okay. So this is what will keep things from segregating as fast. So is to have these integrals. The nice thing is they're exact, so you don't have to argue about the form. Okay, the computational approach then, we're going to use a kinetic-based solver. So this is, again, we've worked on this for 10 years, so it's kind of hard to know all the details, but conceptually what do? We do operator splitting. Kinetic-based solver, we do free transport. So if you go back to the equations that I showed you here, I'm going to get rid of all the terms, and I'm going to first do a step that's just free transport. And free transport means we flux with the velocity, and you get the velocity update with this flux, the temperature update with that flux. And that's, again, just due to the fact that the particles are moving. It's free transport. Why do I use the kinetic-based solver? I'll show you later. Well, it's very easy with the kinetic-based solver to have consistent realizable moments. And the moments here that I'm mainly interested in this one, and this is closed, it's going to be fairly easy. And then for the rest of this part, we use a two-fluid solver. So you could read it with open foam, but you could use your favorite two-fluid solver to solve for the collisional fluxes, the coupling terms, and then the coupling with the gas phase. I'm not going to talk about that too much because that's a traditional CFD thing. The reason why it doesn't affect the realizability and consistency is because that comes from here, and there's no other terms on this equation. Okay. So the second part is what's quadrature-based moment method. So quadrature-based moment methods is how to solve this kinetic equation in a smart way. I mentioned earlier you could do a direct solver by discretizing phase space. In this case, we have a 7-dimensional because we have mass. So here I just have velocity. And then if you're only interested in moments, you would integrate over the solution to get the moments. That's very expensive. You can do that, but it's expensive. And so quadrature-based, you get the moment equations that I showed you. You use a standard CFD solver or one adapted to what you're interested in. Quadrature reconstruction of the density function, so I call it n star. And then any place you can't get integrals, to be exact, you use the n star back in the equation. So it's a quadrature-based means there's many ways to reconstruct. Quadrature-based is one of them. So we do this, and it has nice properties for the numerics. Okay, but the basic idea is you reconstruct given moments, you reconstruct a density function that gives you the same moments, and you use that to do closure. An obvious example is the isotropic Gaussian. Maxwellian is a closure, right? So if you say, I just know the Granite temperature, you make a Maxwellian, and then you close the integrals. That's the classical way. Okay, so if you're doing quadrature-based moment methods for velocity, so what are the requirements if you want to go beyond a Maxwellian and you want to do something more complicated? Well, in general, you want your density function to be non-negative because that's the mathematical property. It's a density function. Can't be negative. We also want it to work for all realizable moments. That means even extreme cases where you have two crossing velocities, where you have two delta functions, you've got to be able to reconstruct two delta functions. You can't replace it with a Gaussian distribution, for example. So all possible sets, it's got to work. And then the nature of reconstruction is that if you have n star, it has to have the same moments as you put in. So you can't modify the moments. You give it moments, the distribution has to reproduce it. Okay, so there's many that can do that. You want it to be fast. Why do you want it to be fast? Well, we're going to do two or three inversions, typically in every computational step at every grid cell. So you have to be able to do that. So you want it to be fast. And this is one we haven't talked about very much. We talked about it internally. This is a real math issue. You like the closure for the free transport flux, which is moment k plus 1, to be hyperbolic. And I'll try to explain that. Hyperbolic basically means that, well, it has to have real eigenvalues so that everything proceeds on real finite velocities. Okay. And I'll show you an example of that in a minute. So here's some methods that you know probably. I gave a talk a month ago at a Lattice-Boltzmann conference. And well, we do this too. Why don't we use discrete velocities? Well, if you use Lattice-Boltzmann, what do? You fix the velocities on a grid. Okay, and it's very simple to show that if you choose a certain sets of moments and you compute the weights using Lattice-Boltzmann, you're going to get negative weights because they don't adapt. Just think if your real velocity distribution is two delta functions, the ones that you use for Lattice-Boltzmann don't correspond to those two delta functions. It's going to try to reproduce it, and it's going to have negative weights. It's a linear algebra problem. So that's why we don't use linear Lattice-Boltzmann. Again, this is highly compressible flow. This is not incompressible. Another very good method is entropy maximization. Very good in the sense that it has very good mathematical properties. For example, you can show that restructures are always hyperbolic. The bad thing about it is you have to do a optimization problem to do every inversion, and that is very slow on, right? even on big computers. I worked with someone at Oak Ridge, and he said, oh, it doesn't matter how slow it is. We have all these machines with GPUs. We should just program it to do that anyway. But it still turned out to be too slow. So that's really the problem there is it's nice mathematical properties, but it's slow. And so the quadrature-based moment methods are fast, because the inversion algorithm is fast. And they're guaranteed to be non-negative. That's the quadrature part of it. But the ones that you usually see, the ones that we published at the beginning, were weakly hyperbolic, and I'll explain what that means. Weakly hyperbolic is different from hyperbolic because you have repeated eigenvalues. So you have two velocities that are the same, and you don't have an eigenvector, separate eigenvector, and what happens is you get mass accumulation. It's a well-known mathematical problem, so if you talk to mathematicians, they'll say, oh, this is not good. The original kinetic equation doesn't have this property. It's going to be hyperbolic. So it has to do with how you close. Okay, so how do we do size velocity? So that's just the velocity. For size velocity, we start with moments. And I'm not going to say very much about that because that's a problem that was well known. If you have 4 moments, there's something called the quadrature method of moments that was done in the late 90s by Bob McGraw. And there's an algorithm. It's basically an eigenvalue problem. Given those moments, you get the weights and the abscisses. If they're realizable, the weights are always positive. Okay, so there's an algorithm to do that relatively fast. With just 2, you can do it by hand, so it's even easier. So we use that. We then use conditional quadrature method of moments. And so now this is where you have to remember the things that we defined earlier. So these are the things you're transporting, the script U's and script T's. I said we needed 2 of them for each. So what we're going to do is we have basically think you have 2 particle classes, W1 and W2, with 2 sizes, C1 and C2. And you want to know what their velocity for size 1, velocity of size 2, ground and temperature size 1 and size 2. If it's a system of delta functions, you can write it as a linear system that looks like this. These guys are now known because it was first step. The weights are known, they're never 0. And so you can invert this and you can get U1 and U2. So it's well behaved. The fact that you use quadrature, you're guaranteed that the system is invertible. So. Okay, so that's where we get the non-script ones. And then if, for example, if you choose a closure, like an isotropic Gaussian closure, that's what I gave here. Once you have this information, so you know this, you compute these, you get the weights and abscisses, then you can say, okay, I reconstruct my distribution function like this, where you have a Gaussian distribution with granular temperature theta 1 and theta 2, and add them together. So that's a closure, based on the information, it's isotropic Gaussian. Okay, we want to go to higher order, so that was just, we used this, the trace of the second order moments. That's isotropic. In that case, there's no viscosity, so you have to do Chapman-Enskog to get the viscosity equation, classical. If you wanted to not have to do the Chapman-Enskog at that level, you can do the full second order tensor. So it's six components, full second order. It's called anisotropic Gaussian. You have to add 5 more moment occasions. I didn't write them down, but you get them in the same way. If you want to have particle trajectory crossing, you need this conditional QMOM, so you get third order, so you can have things go through each other. At these two, neither of these will allow you to go through each other. This one will go through each other. It's weakly hyperbolic, so we used that for many years. We didn't bother with it. It was weakly hyperbolic, although in our simulations you can find points where you get high mass if you do grid refinement. So the one we're using that I want to show today is the conditional with fourth order, so we made it hyperbolic. Okay? But the idea is the same. In general, higher order closures capture more of the non-equilibrium physics. If these systems are very, very collisional, this is enough, right? This is enough. But if you have dilute systems, then they become, the distribution functions are far from Gaussian, so you need more non-equilibrium physics. And the most non-equilibrium thing you can do is particle trajectory crossing, because they don't see each other at all. The general problem with that is that as you go up with more moments, you've got to have metanumerics because realizability becomes an issue. Okay, so how do you get hyperbolicity from a moment closure? So this we started working on this, I guess, 3 years ago. You can pose a problem like this. It's a very simple mathematical problem. Let's say we want to close at fourth order. So we want to transport moments 0 through 4. This system is realizable as long as the fourth order moment, which this is just standardized fourth order moment is eta, and standardized third order moment is q. So as long as the fourth order and third order moment have this property that eta is greater than or equal 1 plus q squared, so it's a parabola, it's well known. So you can, once you have M3 and M4, you can compute eta and q, and you can check this, and as long as it's greater, then your moments are realizable. If it's equal, then it's weakly hyperbolic, you're on the border, and so it's really a delta function. Okay, so we're going to assume that we start out with realizable moments, and then we have our closure problem is that the free transport term, when we compute it, has M5. So if you do the integrals, the equation that transports M4 is spatial flux of M5, right? So that just comes from the integrals you're doing. And you want this choice of M5. So basic problem mathematically, how do you choose M5 such that this system is hyperbolic for all realizable M4? We did it different ways. It turns out you can actually compute the eigenvalues and eigenvectors for the system. If you compute the central fifth order moment like this, so I close basically, if I know this, then I know this. I can then compute the eigenvalues and eigenvectors. And here they are. So this is the mean velocity. This is the second order moment. And then these A's and Q's are just the ones that come from the third and fourth order moment. So here's the eigenvalues. You've got one that's moving with a mean velocity, one plus and minus here, and a plus and minus there. So there's 5 eigenvalues. And as long as this is true, well, if this is equal, then these go out, and so you have weakly hyperbolic system. But if this is bigger, then all the eigenvalues are different, they're distinct, and that's what means that they're real. There's no negative square roots and distinct, so that system is hyperbolic. Okay. So I think we got lucky, because usually when you do closures, moment closures, notice I didn't say anything about quadrature here. There is no quadrature. This is a moment closure M5 that gives you something that's hyperbolic. We started out as we did it as first as saying, well, if we have three delta functions with different weights, how would we get this? And it turns out you don't even have to do quadrature. You get it this way. Normally, choosing M5 that's linear is very difficult to find something that's hyperbolic. So. Okay, so it has all the properties that we need. We'll never get delta shocks. It'll always work for all the values of the moments. Moreover, it's simple to implement in a kinetic-based solver. So how do you do it in a kinetic-based solver? So this is the thing that will allow us to have consistent realizable moments. So we have this flux that M1 through M5. M5, it's closed in terms of the lower order moments. We know the eigenvalues because we were able to compute them analytically. So we know what they are. And so we then can define these fluxes. Let's define these fluxes in terms of the eigenvalues. So the eigenvalues is the speed with which information is being propagated. So we're going to use those with upwinded methods. So the positive eigenvalues, the negative of course, you add them together. It's just eigenvalues to the power I plus 1. So that's the speed. And then we're going to use the weights. We're going to have weights. And then M0 is just the mass. Okay. So this is how we're going to define our flux in terms of the known eigenvalues. So the most important thing is are the weights here positive? And it turns out when you write the system, setting this equal to that, you get a linear system like this with 4 weights. The weight 0 turns out to be 0, so the velocity of the weight of the 0 velocity. And it turns out these are always positive. So it turns out the system is well defined with these fluxes. So we have now we know how to do the fluxes, we know how to do the eigenvalues, and we know how to do it and make it realizable. Okay, so let's look at some examples. So there's a lot more. You put this in a finite volume code, you do the integrals, et cetera, and then you can do examples of simple problems. And this is the typical mathematical problem that you look at when you look at distribution functions. It's called a Riemann problem. Notice there's no collision or anything over here. Those are fairly simple, well, simple in a certain way, but in terms of the fluxes, this is the term that causes problems. So we have this moment system which we close with this hyperbolic QMOM. Why are these problems interesting? Well, the mathematical form, you can get the exact solution given the initial conditions. So if you have the initial conditions, so you can check and see how good your method is. Basically, you initialize them on the plus and minus x-axis. And so what I did is I took for x, negative x, we have a Gaussian distribution function with a positive velocity. So this is going to move to the positive direction with a variance that's given by the Mach number. And then the stuff on the right-hand side has a negative velocity. So these are they're going to run into each other. They're going to go through each other because they have opposite mean velocity for the same Mach number. Mach number is just the square root of the speed of sound in the system. If I take the Mach number to infinity, then I basically have no variance. So I just do 2 delta functions moving through each other. Okay. Okay, so we can solve this with this closure. Here's what it looks like. So these are moments. You can see the things are moving through each other. There are 4 speeds, non-zero speeds, so the eigenvalues, you can see them. Here's this velocity, there's a velocity here, and so you can see all of the shocks in the system. So the M0, M1, M2, M4. So you can't really, you can't really see much from that, whether it's working or not. It's best to look at some of the other moments. C2 is a portion of the granular temperature. S3 is skewness. S4 is kurtosis. And then H4 is the Hankel matrix of order 4. As long as this is positive, the system is realizable. So what this is telling us is we start realizable with a Gaussian over here, and it stays realizable, so which is what we expected from our fluxes. And here's what it looks like in terms of the weights and the abscissas. So you don't really use these as output. What you got output is the moments. But you can see the flux weights are always positive, and you can see the 4 velocities, with which in this blue goes to this one. So you can see how much weight is on each velocity as they propagate through the system. And so this is the mean density, the mean velocity. So that's at a fairly low Mach number. So you have a large distribution between them. If you go up to a Mach number of 30, where there's just really like 2 delta functions, now you can see that you get a very sharp, and so all of the abscissas are almost at the same velocity. And if you look at the Hankel matrix, it's Gaussian and it goes really big, which is okay, but it's nearly 0 behind, saying that you're getting close to the edge of the moment space where you have 2 delta functions. Okay, so that's how you go to higher order moments. That was in 1D. How do you do 2 and 3D? Because 1D is usually simple. 2 and 3D is harder. 2 and 3D, we took a page, I guess, from Lattice-Boltzmann, and we say, well, let's use this conditional method that we developed earlier. And in 2D, we'll have 9 velocities, and in 3D, we'll have 27. The difference with Lattice-Boltzmann is our velocities will move. None of them are constant. We have to fix them on every time step based on the moments. So we need to take, this is an earlier version we had conditional moment closure, conditional quadrature method moments. We didn't have what I call symmetric moment sets, meaning we didn't treat all moments equally. We had certain directions that were favored. So now you can see we're going to control moments that are everything's symmetric. It would be 3 and 4 in the 2D, and then in 3D we have 16 moments. So now when you go to a math conference, they say, oh, it's symmetric, it's okay. You're not treating things asymmetrically. 2D and 3D, you can actually show that the system is hyperbolic. It's much harder to show hyperbolicity, but you can do that. And you can also get the degenerate cases, meaning when you reduce this, instead of 27 velocities, remember, if you want to do a crossing, you don't need 27 velocities to do a crossing, you just need 2. And so when you do this, it has to degenerate correctly down to with 0 weights on the other velocities. And so that works too. Okay, so let's do a 3D Riemann problem. So the same idea, but now we've got, it's a 1D in space, but 3D in velocity space. So now we have a correlation between the different components of velocity that are being transported. We use this 3D conditional hyperbolic method. So we M5, which is closed. We do the same thing, splitting it into 2 parts. We have the plus and minus. And then the difference in 3D is now we just don't have one second order moment. We have a full 6 of them. And so we can give different covariant structures. How are the velocities correlated among themselves? They can be uncorrelated. They can be isotropic, uncorrelated, Maxwellian. They can be perfectly correlated, where they're all just on a line. Or they can be partially correlated. And the thing is that with this Riemann problem, the correlation structure doesn't change, because you're just transporting it. It's a transport problem. There's no interaction. There's no collisions. And so if the method's going to work, it's got to keep the correlation structure constant as you transport. Okay, so here's the same thing with the 16 moments. Again, this is uncorrelated velocities. If you want to, how do you know it's uncorrelated? Well, you can look at these cross velocities here. This is a covariance 1, 1. You can see they're all 0. So that's if you're used to looking at moments, you can see that. For a normal person, it's probably not obvious. But if you look at the 3 and the odd moments, they're 0. So that seems to be working okay. It didn't blow up. It's better to look at the weights and abscissas. You can see a lot more information. So this is the uncorrelated case. So what you're looking at in the U direction is simply the hyperbolic system I showed you earlier. It just does what the 1D system did. And you can see it goes through. You create an abscissa in the middle, so you get the 3 here. But for the V and W, they're completely uncorrelated. So they just get transported along, and they're just isotropic Gaussians. They've got 1, 2, 3. There's 9 abscisses there. You can't see them because they're on top of each other. And the mean velocities don't change. And so it keeps the correlation structure. If the velocity is initially uncorrelated, it stays uncorrelated. If you do perfectly correlated, so think in velocity phase space, there's the line. So everything is on 1D, really. It's really a 1D problem, but you're solving in 3D. So I just can choose whatever angle I want. So I chose some particular angle for my covariance, but it's perfectly correlated. Correlation coefficients are either 1 or -1. It's a little bit, you can now see that there's some correlation between them, okay? But again, it's hard to see actually what goes on. If you want to have perfect, if you go to look in the abscissa space, though, it's quite clear now that they're perfectly correlated, because this is the 1D problem, and then you can see that the second direction and third direction are exact replicas of the first direction, just on a different angle, okay? So it's perfectly, and likewise, the mean velocities are just linear combinations of each other. Okay, so that's hard to get if you use Lattice-Boltzmann or any other thing, because there's no guarantee you're going to stay correlated if you do that. Okay, the last case is the partially correlated. This is where you're going to see that there's really 27 abscissas. Here you can see again the moments, and so this is if you look at the abscissas in this case, now you can see in 1D you see the 3. Here you see 9 abscissas. And then over here in the third direction, you see all 27 of the abscissas. So it degenerates correctly to the. Okay, we then did with Ravi Patel, he did implemented this in NGA code of Olivier. And we said, okay, will it do trajectory crossing? So we're solving for all these moments, 16 moments, 27 velocities. And you can see the method, it knows when it crosses, and so it takes care of it perfectly. So we're able to do the degenerate case of crossing. I think you use a high order method for this. Olivier, I think you use a second order muscle scheme or something. Yeah, you use that because it's not so diffusive as usual. He also did, this is a problem that we worked on and Marc Masseau's group has worked on. This is a spray problem where you're spraying in droplets here and here. It's very dilute and they're being pushed towards this plane. And if you use an anisotropic Gaussian, it fills in the middle of these because they can't cross. But because we have a third or fourth order closure, we can see we get the crossing, and so it reproduces the exact solution, which is the white traces. The cost is not very much more. It's not much more expensive to add the other moments. So because we have M3, we can do that one. And then in 3D, this is I think this was the first order upwind, because this is the earliest one he did. So you can do particle trajectory crossing in 3D. Earlier methods we had, you had to kind of know which wind is, when you did the inversion, you had to know something, how to choose some rules. But now it figures out the angle arbitrarily. You don't have to give it any information. It's already in the moments, and so it figures it out. Okay, so let's go back to the gas particle flow problem. So again, I'm going to go back to the simplest closure. I'm not going to use hyperbolic closure. I'm going to use isotropic Gaussian closure. So I'm going to go back to this MS, US, and TS. The goal of this was to couple with an existing solver that we had an open foam, but you use your own solver, because we had a good solver for gas phase and the coupling and the dense limit. So that's what we were interested in. So we wanted to do that. So we did that, and then we wanted to make sure, though, that the moments were consistent and realizable. If you just do it directly, it doesn't work unless you're first order upwind. So we had to do our own fluxes for the kinetic-based scheme to do the free transport fluxes. And so again, it's like I showed you earlier. You take this term and you integrate it over the finite volume. The finite volume then becomes fluxes to surfaces, so you integrate over all the surface and all the abscissas, and you take upwinded velocities. Okay. We did the collisional fluxes and the source terms directly in open foam using the semi-implicit method. And so far, we have not tried to do the frictional regime. That's the hard part, but it has nothing to do with this, because frictional regime is really how do you do a polydisperse frictional model that's predictive. So I'm not sure whether one exists. We can discuss that. So we're going to mainly look at dilute. So all of this, again, if you're in a frictional regime, you don't have kinetic theory anymore. You don't need the velocity distribution function, right? Because you're in a temperature 0. So this is, you would just go back to a simple, even isotropic Gaussian is more than you need. Okay, the algorithm, I don't expect you to see this, but this is the idea behind how this works. So I put the red part's the first part. So you initialize, you do free transport, and then you have to do some some recalculation of the weights and abscisses. That's why you need a fast method to go back and forth. So kinetic-based scheme updates the weights and abscisses and the velocities. Then we do the implicit part for the collisional fluxes and source term inside open foam. We do some iterations from step 2 to converge for the semi-implicit method. And then we end with a gas phase and then go back. Okay. If you use a denser solver, the gas phase has to be more coupled into it because of the coupling between is stronger. But here we don't need that. Okay, so let's look then at the different cases and see if the solver is working. The key here is the realizable moments and the consistent moments. And so we did, to test it, we did this riser. This is a periodic riser flow, similar to what Jesse did with Euler-Lagrange. What I showed you at the beginning, the volume fraction of the particles on average is 2%. We took a binary system, 100 and 300 microns, with a mass ratio of 27. Okay. Equal mass fractions, so the density is constant, so it's equal volume fractions. The number is a lot different because it's 27, a factor of 27 more smaller particles. It's all periodic and it's gravity driven. So the test here is to see, well, if we start out with a system with 2 particle sizes, but we don't tell it we have 2 particle sizes. We do all the moments and we solve for the moments. Will the solver be able to figure out we just have two sizes? Okay, so you do this, you solve the system. You can solve it up to a steady state. This is just a snapshot, just to show you what the velocity moment or the size moments look like. The clusters, it turns out, all the particles, even though they have different sizes and masses, they tend to cluster together. And that's because of the coupling with the gas phase tends to push them all together. There are small differences. You can see number average. You can see differences compared to the third order mass average. So there are differences in moments. So it's quite a complex flow in time. It's time dependent. If you use those to calculate weights and abscisses, so this is the important part, you get constants. And it turns out you do, because of the flux space, the fluxes, the way you calculated them, you get a very complicated field for the mean diameter. But if you just calculate the diameter of each, or the mass of each size, they're constant. We didn't impose that. We get with the moments in, and if you don't do the fluxes correctly, you'll get fields here that are not constant. Okay, so unless you use the kinetic-based flux, you can't get that. So this shows it's consistent because of the kinetic-based. Okay, here's just some statistics for those of you interested in gas particle flow. We're plotting them versus the volume fraction, instantaneous volume fraction in the field. The clusters are here. These are the things you actually see when you look at it. You can see all the clusters. They have all the particles of the 2 different sizes have nearly the same velocity. In the dilute regions away from clusters, you get some of the smaller particles are moving upward. They're being moved upward because the gas is going much faster there. Likewise for granular temperature, in the clusters, the granular temperature is very low. And then over here, if it were at equilibrium, there'd be a difference of 27 between. Here it's of course not 27 because of the exchange, but you can see in the dilute regions you get a big difference in granular temperature. So the statistics you can get out of the calculation. Okay, so let's then look at a harder problem. Okay, now this is a test of realizability. Is the method realizable? So to do this, we took basically the same problem, except now we filled the domain with a density function on the top. So the top half of it has a density function where you have 2 abscisses, because we're using just 2 delta function representation of 300 and 600 microns. We put all the big particles up here. Okay, and then on the bottom, we put 100 and 200 micron particles. And so now we'll let them fall. What should happen? Well, it's as if you had 2 distribution functions that are going to mix together. So you have a distribution over here, and in the end they're going to mix, and you're going to end up with the same, but they're no longer going to be separated in space. And so the method should be able to do mixing without any problems. If you use direct quadrature method of moments, so if you notice over the last 10 years I haven't done very much direct quadrature method of moments, you can't do this problem. It can't do this problem because the moments are the conserved quantities, and so you flux conserved quantities, whereas weights and abscisses aren't. And so if you try to put them at an interface between the two, you'll get a shock and it just doesn't work. And so if you do it this way, it works fine. Okay, so we're starting out with that and see what happens. So you can see the mean particle size dropping down, and it takes some time before the clusters start to form. But you can see this. Whether any of this is physical is, I don't have to say, this is a math conference. So you can see it does end up being the clusters that we saw earlier. This is the mean particle size. These are alpha p, the mean, well, the mass-weighted volume fraction, mean velocity, and granular temperature. So it ends up being a cluster flow at the end. So that's kind of what you'd expect. Here are the size moments, so the 4 moments that we're solving for. It's harder to see because of the scale, but you can they're going to evolve in time. They remain realizable for all time, so we never have a problem if we're not able to do inversion for that because we have the kinetic-based scheme, and eventually it finishes up being cluster-induced turbulence. And then if you look over here, now this is the weights and abscissas that correspond to the size. So we take the size moments and we compute the inversion to get alpha, the volume fraction for size 1, volume fraction size 2. Again, these are not the actual sizes, these are the local sizes viewed after mixing. Okay, so these change in space and time. It's interesting to see that with time, this is a closed system. It just becomes well mixed in time, and so you can see the 2 abscissas that you end up with at long time actually become uniform, and there would just be the 2 abscissas that you would get by taking the distribution function, the original distribution function, and taking the 2 abscissas. So all of the action that is in the volume fractions of how these move. So once fully mixed, it works, and there's no problem with approaching it from the unmixed state. Here's the abscissas. So this is probably. So these are the actual velocities. These are the velocities we solve for, and these are the ones after inversion. So you have to look at these a long time to see the difference. So think of these as the velocities of the sizes. These are the weighted velocities. And there's some small difference, but it's hard to see much difference. But it's just to show you that they're different mathematical entities. These are just post-processing. At the very end, you can see these are the bigger particles. So the red part's the upward velocity, and so you'll see that the smaller particles have a tendency to have more upward velocity at the end. And then likewise for granular temperature, this is the same. So these are what you solve for. The number-weighted and mass-weighted granular temperature is what you solve for, and then you can get the inversion gives you for each size locally, and so you can see that evolves. Okay, I'm almost out of time, so we did the same thing for vertical channel. So kind of get closer to reality. We use the same idea. We have this is the binary system. We checked that one first. Here you get particles that accumulate near the walls when you put in walls. So with wall boundary conditions. So here's some time averaged profiles of what we get. So 100 and 300 micron particles. You can see here's the volume fraction overall. The total volume fraction is here, and you can see the most difference is right at the walls. So the heavier particles, or lighter particles, tend to accumulate at the wall. The heavier particles tend not to, and it's mainly responsible due to the granular temperature. So I think it's the big particles have more momentum. They hit the wall and bounce off. They have higher granular temperatures. They tend to be pushed away. In the center, it tends to be more uniform, and you can see there's a difference in smaller particles on average. These are kinetic energy for the mean velocity in the gas phase and the kinetic energy in the gas phase. Okay, so there is a Stokes number effect then on the distribution. Okay, so what are some open issues? So what haven't we done yet? I guess is and what's the challenges? We haven't yet. Well, we really started this project to have a dense multi-fluid solver. That's why we did the isotropic Gaussian, because we wanted to repeat what's done in single-phase flows. We're still not happy with the way it works in the frictional regime. And it has to do with monodispersed. It works great, no problem. But when you do polydispersed and you put in how the frictional regime works for polydispersed particles, it tends to be very unstable. You get granular temperatures that blow up and things like that. It doesn't look very nice. So I really think as a community we need to work on that. Maybe we need to take a page from granular flow. So in dense regions in granular flow, they use volume of fluids method, and they use with constant alpha p, and those tend to work much more robustly. And so we could use a dissolver like that for the dense regime. Instead of, what happens is that the speed of sound goes to infinity. So if you use one of these direct solvers, you've got to have a very small time step or something to control it. So if we could get around that, just take it to the limit where it's incompressible, it would be better. The size condition, SciQmon, that's something we know how to do, we just haven't done it. And so that's to go up to fourth order with crossing. This part is, we've done this for monodispersed particles, a hybrid solver. So we wanted a solver that works in very dilute regimes where standard kinetic theory models work, and then very dense, or very dense where standard theory models work, and then particle trajectory crossing. So we did a paper on how to do that. That's you just do flux splitting. And so this can be done, but not until this is done, because you need the dense solver. A constant issue is how do you get higher order? The simulations that I just showed you were all first order upwind because we didn't try to do anything better. But we'd like to go to high order methods, spatial methods, to get less numerical diffusion. And you have to do this on obviously unstructured meshes, and it has to work with all the moments. Again, as I mentioned at the very beginning, once you go to high order, it's very easy to have, due to the numerics, to have non-realizable and non-consistent moments. So that's, we know we have some ways to do it, but we'd like more ways. In general, I guess in the whole area, we need more accurate models for aggregation growth. I think Daniele is going to talk a little bit about that. Yeah, he was supposed to talk after me. So, so that's an important area for applications. The numerics work fine in the applications. And then in general, I think in the kinetic theory model, we just need to add more physics. Physics, we like pseudo-turbulence in the gas phase, things like buoyancy, added mass, things like that, and using the same solvers. Okay, so all of this is probably too complicated for someone to do on their own. Certainly it took us a long time to do it. So we have this OpenQBM project that was funded by NSF up to this year. And basically all the methods I just showed you are in this project. So if you use you're an OpenFOAM user, you can go to this website and you can choose the system you're interested in. I just loaded up all of my talks for the last 10 years here too. So if you want to hear this talk again, you can go there because it's on all the talks and how things developed. Alberto Pasalacqua is the person that runs this mostly, and so he's very good at OpenFOAM. So if you have OpenFOAM issues, he usually responds immediately. I don't think he ever sleeps. So. Okay, so here's all of my collaborators. This is the book I wrote with Daniele that tells you kind of more of the theory. The implementation in OpenFOAM was all done by Bo Kong at the top and Alberto. And then the hyperbolic stuff was done with Central Superlac and Frédéric Laurent and Marc Massot and VA. And then the part with the NGA was done at Cornell and the NSF project. And of course, Jesse gives us all of the data that we use for comparison. Okay, so thanks for your attention. Happy to answer questions.
We have a few minutes for questions.
Well, I have